the most important statement of the central limit theorem is the fact that it will slowly become a normal distribution. Now, when you say a large sample size, what large, how large should it be? Now, you can do this experiment numerically. Take a very badly skewed distribution, for example, something like this. If you take a very bad distribution, something like this, a distribution like this, as bad as this, there can be some samples here, nothing here, some samples there, nothing else. So, even for that bad distribution, if you take 10 samples and obtain the mean, it will be somewhere here. If you take another 10 samples, it will be somewhere around here, it will be another 10 samples, it will be somewhere here. So, all that you will get some distribution, but it might not be a very good approximation to a normal distribution. But if you take instead, if you increase the number of samples each time, you will find that as you exceed say 20, it is more and more resembling a normal distribution, and beyond 25 it is practically a normal distribution. And because of that, we normally take it for granted that beyond 25, if you take further readings, it does not improve the approximation to a normal distribution. So, it suffices to take 25 as the number. So, large essentially means n should be greater than or equal to 25, at least 25. And I would strongly advise you to do this experiment numerically once by taking random samples from this kind of a distribution and obtaining the mean and finding how the means will be distributed. You will find that it approximates a normal distribution at as n exceeds 20, and after 25 there is no further significant improvement in the approximation. So, how large? 25. Okay. Now, on that basis, let us do an example. With the help of that, you will realize the advantage of the central limit theorem. Example. Suppose there is a population with mean 2. I will not specify 2 in units, because it could be any unit. If you are measuring the height of a population, it will be in meters. If you are measuring the weight of a population, it will be in kilograms. So, whatever it is, this is I will specify that as a unit independent number, and standard deviation 0.7. The distribution within this population is unknown. Suppose you do not know that. Now, suppose you take 20 samples out of that, population, and then you take 20 samples out of the population, and we are trying to assess what will be the probability. So, what will be the probability that the sample mean will lie beyond say it was 2, so let it be 2.2. So, as bad as this. So, how do you proceed to attack a problem like this? It says that the population has mean this, standard deviation this. So, if you have taken 20 samples, you get some x bar sample mean. If you again take another 20 samples, you will get a different x bar, the sample mean, and if you keep on taking such 20 samples again and again, you will get a distribution of the means, and the central limit theorem asserts says that since 20 is close to the necessary number 25, that it can be approximated by a normal distribution. It can be approximated by a normal distribution with mean same as the population mean 2 and standard deviation will be the population standard deviation 0.7 divided by square root of the number of samples you have taken 20. Okay. This comes to be 0.156. So, that will be the standard deviation of the distribution of the means. Now, we have to face the question, let me get some space. Yeah. Now, we have to face the question, what will be the probability, let me write here, probability P that x bar lies above 2.2. This is the question asked. This is equal to probability that x bar lies above lies I'll write it a bit differently. 2.2, how different is it from the mean? 2. This is 0.2 divided by the standard deviation, which is 0.156. This many is equal to, it will become 1.28 standard deviations. I will not write yes. This many standard deviations above the mean. So, 0.156 is the standard deviation and 1.28 standard deviation would be somewhere here. We are actually trying to find out. So, this is 1.28 standard deviation and we are trying to find out the area under the curve in this range. This is what we have to find out. Now, this value, the multiplier of the standard deviation is called the z value. In American pronunciation, it will be z value, but let me go by the British pronunciation or Indian pronunciation, the z value. The z value is the multiplier of this. Now, people have integrated the normal distribution curve up to certain values and have tabulated that, that is available as the z table, and we have to read off the value from there. Let us do that. Here I have plotted the z table and this is the normal distribution and here is the z value. and what the Z table gives is that the area under the whole curve is 1 and how much of that is contained to the left of that Z value. So, that is what gives the what is given in the table. So, now we have to read off the table the area to the left of 1.28, which is the Z value. So, when we do that, 1.2 is here, and if we go further to the right and 0.08 is here. So, we get 0.8997 as the value, 0.8997 as the value that we have to use, and I will go ahead with that value to the rest of the calculation. So, let me write it afresh. The probability of x bar lies 1.28 standard deviation above the mean. This is what we needed to calculate, and we have found that that value is well, let me plot it once. It is a normal distribution because the number of samples was close to 25, 20 it was, and here we know that this value is the population mean, which was 2, the standard deviation was 0.156, and divided by square root of n was 1.28. So, we had to calculate the area here, but we have actually calculated the area to the left of that. Okay. So, this area has turned out to be 0.8997. So, this area will be 1 minus 0.8997 is equal to, it will be 0.1003, which is approximately, this is about 10.03%, 10%, which means that for the problem given, the actual the mean of the population was 2, but by obtaining 20 samples, I stand a chance about 10% chance of obtaining a mean which is above 2.2. So, there is a high risk of committing a error by making the measurement that way. But suppose we increase the number of samples to 50. So, suppose we increase the number to 50, then what happens? Then we get this curve a more narrower distribution. It will become a narrower distribution, it will become a narrower distribution, and in this narrow distribution the mean will be 2, the standard deviation will be 0.7, the original standard deviation divided by root over 50. Now, this is equal to 0.099, and using this, if we obtain the Z value, then the Z value will become Z is equal to the way we calculated 2.2 minus the mean 2 divided by the new standard deviation, which is 0.099, then it comes to be about 2.02. And for this value, if we again refer to the Z table, and then we find that the area under the area to the left of the curve of the Z value, in this case becomes 0.9783. Therefore, the probability of x bar lies above 2.2 will now become 1 minus 0.9783 is equal to a small number. It will come to be 0.0217. So, around 2%, 2.17%. So, the chance of committing an error will be less. And notice that all these we are being able to calculate because the central limit theorem asserts that the curve ultimately we get for the distribution of the means will be a normal distribution. So, all this could be calculated using that fact. Now, the value that we get by dividing by square root of the n, that standard deviation of the sample means is called the standard error of the mean. Okay. So, this is an important thing that we get, the standard error of the mean is let us call it sigma, but sigma of what? Of x bar. That is our sigma divided by square root of n. This is the standard error of the mean, and this gives an estimate of how much error can we commit by actually obtaining samples and talking about the means obtained from the samples. Let us illustrate that again with another example. Now, another example, suppose you have measured some quantity uh, 36 times. I am using a square number so that it can be, you can obtain square root easily, times and have obtained a sample mean we are calling it x dashed, you have got it 112 this, and a sample standard deviation, how much is it? S equal to 40. Now, the question is, what is the probability that the actual mean, the population mean, we call it mu, lies in the range is given between 100 and 124. 100 is this mean minus 12 and 124 is this mean plus 12. So, this is how we have defined the problem. So, notice that in this case we have only the result of the sample available to us, and we do not know the actual population mean or population standard deviation. In that case, can we estimate some range in which the population mean will lie, and with which probability will that happen? So, notice again the line of argument. If we repeated the experiment again and again, every time taking 36 samples, then we will get, since 36 is bigger than 25, we will get a normal distribution of the sample means. So, the sample means will have a normal distribution, something like this. So, this is the mean of the not of the sample, but of the population, and it will have a standard deviation which is the population standard deviation divided by root over 36 is 6. So, this is what we can infer using the standard central limit theorem. Now, what we are trying to find out is the probability that the actual mean mu lies in this range. Okay. So, probability of mu lies in the range. This is 100 to 100 means actual x bar minus 12 to x bar plus 12. This is what we are trying to find out. Okay. Now, this distribution we do not know really, but we have to try to somehow obtain the z value, and for that we need to find out the distribution, the standard deviation of this distribution, but we do not know this number. This number is out there. This number is of the population. We have measured only the sample. But the best we can do under this situation is to use this sample standard deviation as an estimate of the population standard deviation. So, in place of sigma, we do not know the sigma, but we will substitute the value that you have actually measured, which is 40. So, we get the sigma of the x bar as 40 divided by 6, which is 6.67. So, we have to now find out mu lies within what range of the standard deviation. So, we need to find out. So, this is the let me write it this way, P probability of mu lies within 12 of x bar. Okay. Now, notice here is a value in the whole range, here is a value mu, and here is a value x bar. We are trying to find out, we have found x bar, we are trying to find out how far can mu be from x bar. Now, this is the same as how far can x bar be from mu. Therefore, we can also write this as probability that x bar lies within 12 of mu, right. Now, this is equal to probability that x bar lies within how many standard deviations? It will be 12 by this 6.67 of mu, and this number is the z value. In this case, it comes to be approximately 1.8. Again, if you refer to the z table and read out from this 1.8 number, then the area to the left of that. So, 1.8 standard deviation would be somewhere here. Okay. So, we want to find this area, and this side and the other side. So, we want to find this area, this total area actually. So, this is in the positive side, this is the negative side. This area we need to find out, but we have actually found from here. If we read out from the z table, then the area to the left, get some space, of z equal to 1.8 is equal to, how much is it? 0.9641. Again have to refer to the z table and you have to read this out. So, now notice here we have read to the left of it. There are two ways of calculating this whole thing. One is 1 minus this thing, you will get this area times 2, that is one possibility. The other possibility is that we have got this area, if you subtract 0.5 is this whole area, then you get only this area, then you just get the twice of that, then it will be within this. Okay. So, we need to find out how much area is contained excluding these two tails, okay, within this area, that can be found this way. So, I will do it the second way. So, 0.9641 minus 0.5. So, this whole area minus this half area is this area. This, now I have to twice this into 2. This comes out to be 0.9282. So, the probability that the mu, the actual mean, will lie within 12 of x bar is this 92%, 93% approximately. So, this way, even without calculating, without actually obtaining infinite number of readings, by taking a finite number of readings, we can infer something of interest regarding the character of the population mean. And that this method actually will carry through in much of the measurement process that we will come across. I will come to that later. So, you see, we have obtained answer to two questions that we asked right in the beginning of the course. The question was, how many readings do we need to take in order to make a confident estimate of the mean? The answer is 25. Now, who gives this 25 number? It is actually empirically obtained. We have tried it out and found that that number works, in the sense that by increasing beyond that number, we do not gain much. We have ultimately obtained a value which is which, if repeated many times, will give a distribution of the means which is a normal distribution, and from that normal distribution we can extract all the information. And the most important information we extract is the standard error of the mean, which I just said. I'll just call it SE, standard error of the mean, is the standard deviation, the standard deviation of of the readings obtained divided by square root of the number of samples. In case of a physics experiment, the number of samples means how many times you have conducted the experiments and how many data points you have got. So, this is a very important quantifier that we will use many times in the next few lectures. Just keep this in mind. This is the standard error of the mean. Okay. With that, we will close today and we will continue with that in the next class.